Multiplication is one of the four elementary, mathematical operations of arithmetic, with the others being addition, subtraction and division. The multiplication of two whole numbers, when thinking of multiplication as repeated addition, is equivalent to adding as many copies of one of them as the value of the other one. Normally the multiplier is written first and multiplicand second, though this can vary and sometimes the distinction is not very meaningful. For example, 4 multiplied by 3 can be calculated by adding 3 copies of 4 together. Here 3 and 4 are the factors, and 12 is the product. One of the main properties of multiplication is the commutative property. Adding 3 copies of 4 gives the same result as adding 4 copies of 3. The multiplication of integers, rational numbers and real numbers is defined by a systematic generalization of this basic definition. Multiplication can also be visualized as counting objects arranged in a rectangle or as finding the area of a rectangle whose sides have given lengths. The area of a rectangle does not depend on which side is measured first, which illustrates the commutative property. The inverse operation of multiplication is division. For example, since 4 multiplied by 3 equals 12, then 12 divided by 3 equals 4. Multiplication by 3, followed by division by 3, yields the original number. Multiplication is also defined for other types of numbers, such as complex numbers, and more abstract constructs, like matrices. For these more abstract constructs, the order that the operands are multiplied sometimes does matter. A listing of the many different kinds of products that are used in mathematics is given in the product page. Notation and terminology. In arithmetics, multiplication is often written using the sign times between the terms, that is, in infix notation. For example, the sign is encoded in Unicode at U plus OOD 7 times multiplication sign. There are other mathematical notations for multiplication. Multiplication is also denoted by dot signs, usually a middle position dot. The middle dot notation, encoded in Unicode as U plus 22C5 dot operator, is standard in the United States, the United Kingdom, and other countries where the period is used as a decimal point. When the dot operator character is not accessible, the interpunct is used. In other countries that use a comma as a decimal mark, either the period or a middle dot is used for multiplication. In algebra, multiplication involving variables is often written as a juxtaposition. The notation can also be used for quantities that is surrounded by parentheses or for 5 times 2. This implicit usage of multiplication can cause ambiguity when a concatenated variables happen to match the name of another variable. When a variable name in front of a parenthesis can be confused with a function name, or in the correct determination of the order of operations. In matrix multiplication, there is a distinction between the cross and the dot symbols. The cross symbol generally denotes the taking a cross product of two vectors, yielding a vector as the result, while the dot denotes taking the dot products of two vectors, resulting in a scalar. In computer programming, the asterisk is still the most common notation. This is due to the fact that most computers historically were limited to small character sets that lacked a multiplication sign, while the asterisk appeared on every keyboard. This usage originated in the Fortran programming language. The numbers to be multiplied are generally called the factors. Usually the multiplier is placed first and the multiplicand is placed second. However, sometimes the first factor is the multiplicand and the second the multiplier. Additionally, there are some sources in which the term multiplicand is regarded as a synonym for factor. In algebra, a number that is the multiplier of a variable or expression is called a coefficient. The result of a multiplication is called the product. A product of integers is a multiple of each factor. For example, 15 is the product of 3 and 5, and is both a multiple of 3 and a multiple of 5. Computation. The common methods for multiplying numbers using pencil and paper require a multiplication table of memorized or consulted products of small numbers. However, one method, the peasant multiplication algorithm, does not. Multiplying numbers to more than a couple of decimal places by hand is tedious and error-prone. Common logarithms were invented to simplify such calculations. The slide rule allowed numbers to be quickly multiplied to about 3 places of accuracy. Beginning in the early 20th century, mechanical calculators, such as the Marchant, automated multiplication of up to 10-digit numbers. Modern electronic computers and calculators have greatly reduced the need for multiplication by hand. Historical algorithms methods of multiplication were documented in the Egyptian, Greek, Indian, and Chinese civilizations. The Ashango bone, dated to about 18,000 to 20,000 BC, hints at a knowledge of multiplication in the Upper Paleolithic era in Central Africa. For instance, to find the product of 13 and 21, one had to double 21 3 times, obtaining 1 times 21 equals 21, 4 times 21 equals 84, 8 times 21 equals 168. The full product could then be found by adding the appropriate terms found in the doubling sequence. 13 times 21 equals times 21 equals plus equals 21 plus 84 plus 168 equals 273. Babylonians. The Babylonians used a sexagesimal positional number system, analogous to the modern-day decimal system. Thus, Babylonian multiplication was very similar to modern decimal multiplication. Because of the relative difficulty of remembering 60 times 60 different products, Babylonian mathematicians employed multiplication tables. These tables consisted of a list of the first 20 multiples of a certain principal number n, 2n, 20n, followed by the multiples of 10n, 30n, 40n, and 50n. Then to compute any sexagesimal product, say 53n, one only needed to add 50n and 3n computed from the table. Chinese. In the mathematical text Zhou Bai Suan Jing, dated prior to 300 BC, and the 9 chapters on the mathematical art, multiplication calculations were written out in words, although the early Chinese mathematicians employed rod calculus involving place-value addition, subtraction, multiplication and division. These place-value decimal arithmetic algorithms were introduced by Al-Khwarizmi to Arab countries in the early 9th century. Modern method. The modern method of multiplication, based on the Hindu-Arabic numeral system, was first described by Brahmagupta. Brahmagupta gave rules for addition, subtraction, multiplication and division. Henry Burchard Fine, then professor of mathematics at Princeton University, wrote the following: "The Indians are the inventors not only of the positional decimal system itself, but of most of the processes involved in elementary reckoning with the system. Addition and subtraction they performed quite as they are performed nowadays. Multiplication they effected in many ways, ours among them. But division they did cumbrously." Computer algorithms. The classical method of multiplying two n-digit numbers requires n2 simple multiplications. Multiplication algorithms have been designed that reduce the computation time considerably when multiplying large numbers. In particular, for very large numbers, methods based on the discrete Fourier transform can reduce the number of simple multiplications to the order of n log 2 log 2 log 2. Products of measurements. One can only meaningfully add or subtract quantities of the same type, but can multiply or divide quantities of different types. 4 bags with 3 marbles each can be the overs. 4 bags times 3 marbles per bag equals 12 marbles. When two measurements are multiplied together, the product is of a type depending on the types of the measurements. The general theory is given by dimensional analysis. This analysis is routinely applied in physics but has also found applications in finance. A common example is multiplying speed by time gives distance, so 50 km per hour times 3 hours equals 150 km. Other examples: products of sequences. Capital Pi notation. The product of a sequence of terms can be written with the product symbol, which derives from the capital letter pi in the Greek alphabet. Unicode position U plus 220F contains a glyph for denoting such a product, distinct from U plus 03AO, the letter. The meaning of this notation is given by, that is, the subscript gives the symbol for a dummy variable, called the index of multiplication, together with its lower bound, whereas the superscript gives its upper bound. The lower and upper bound are expressions denoting integers. The factors of the product are obtained by taking the expression following the product operator, with successive integer values substituted for the index of multiplication, starting from the lower bound and incremented by 1 up to and including the upper bound. So, for example, more generally, the notation is defined as where m and n are integers or expressions that evaluate to integers. In case m equals n, the value of the product is the same as that of the single factor xm. If m greater than n, the product is the empty product, with the value 1. Infinite products. One may also consider products of infinitely many terms. These are called infinite products. Notationally, we would replace n above by the lemma scate infinity. The product of such a series is defined as the limit of the product of the first n terms, as n grows without bound. That is, by definition, one can similarly replace m with negative infinity, and define, provided both limits exist, properties. For the real and complex numbers, which includes, for example, natural numbers, integers and fractions, multiplication has certain properties. Commutative property. The order in which two numbers are multiplied does not matter. Associative property. Expressions solely involving multiplication or addition are invariant with respect to order of operations. Distributive property holds with respect to multiplication over addition. This identity is of prime importance in simplifying algebraic expressions. Identity element. The multiplicative identity is 1. Anything multiplied by 1 is itself. This is known as the identity property. Property of 0. Any number multiplied by 0 is 0. This is known as the zero property of multiplication. Negation. -1 times any number is equal to the additive inverse of that number. -1 times -1 is +1. The natural numbers do not include negative numbers. Inverse element. Every number x, except 0, has a multiplicative inverse, such that order preservation. Multiplication by a positive number preserves order. If a greater than 0, then if b greater than c, then ab greater than ac. Multiplication by a negative number reverses order. If a less than 0 and b greater than c, then ab less than ac. The complex numbers do not have an order predicate. Other mathematical systems that include a multiplication operation may not have all these properties. For example, multiplication is not, in general, commutative for matrices and quaternions. Axioms. In the book Arithmeticis Principia, Nova Methoda Expositor, Giuseppe Pino proposed axioms for arithmetic based on his axioms for natural numbers. Pino arithmetic has two axioms for multiplication. Here S represents the successor of y, or the natural number that follows y. The various properties like associativity can be proved from these and the other axioms of Pino arithmetic, including induction. For instance, S, denoted by 1, is a multiplicative identity because the axioms for integers typically define them as equivalence classes of ordered pairs of natural numbers. The model is based on treating as equivalent to x minus y when x and y are treated as integers. Thus both n are equivalent to -1. The multiplication axiom for integers defined this way is the rule that -1 times -1 equals 1 can then be deduced from multiplication is extended in a similar way to rational numbers and then to real numbers. Multiplication with set theory. The product of non-negative integers can be defined with set theory using cardinal numbers or the Pino axioms. See below how to extend this to multiplying arbitrary integers, and then arbitrary rational numbers. The product of real numbers is defined in terms of products of rational numbers. See construction of the real numbers. Multiplication in group theory. There are many sets that, under the operation of multiplication, satisfy the axioms that define group structure. These axioms are closure, associativity, and the inclusion of an identity element and inverses. A simple example is the set of non-zero rational numbers. Here we have identity 1, as opposed to groups under addition where the identity is typically 0. Note that with the rationals, we must exclude 0 because, under multiplication, it does not have an inverse. There is no rational number that can be multiplied by 0 to result in 1. In this example we have an abelian group, but that is not always the case. To see this, look at the set of invertible square matrices of a given dimension, over a given field. Now it is straightforward to verify closure, associativity, and inclusion of identity and inverses. However, matrix multiplication is not commutative, therefore this group is non-abelian. Another fact of note is that the integers under multiplication is not a group, even if we exclude 0. This is easily seen by the non-existence of an inverse for all elements other than 1 and -1. Multiplication in group theory is typically notated either by a dot, or by juxtaposition. So multiplying element A by element B could be notated AB or AB. When referring to a group via the indication of the set in operation, the dot is used, e.g., our first example could be indicated by multiplication of different kinds of numbers. Numbers can count, order, or measure, as the history of mathematics has progressed from counting on our fingers to modeling quantum mechanics. Multiplication has been generalized to more complicated and abstract types of numbers, and to things that are not numbers or do not look much like numbers. Integers is the sum of m copies of n when n and m are positive whole numbers. This gives the number of things in an array n wide and m high. Generalization to negative numbers can be done by, and the same sign rules apply to rational and real numbers. Rational numbers generalization to fractions is by multiplying the numerators and denominators respectively. This gives the area of a rectangle high and wide, and is the same as the number of things in an array when the rational numbers happen to be whole numbers. Real numbers and their products can be defined in terms of sequences of rational numbers. Complex numbers considering complex numbers and as ordered pairs of real numbers and the product is. This is the same as for reals, when the imaginary parts are near 0. Equivalently, denoting as I, we have further generalizations. See multiplication in group theory, above, and multiplicative group, which for example includes matrix multiplication. A very general, and abstract, concept of multiplication is as the multiplicatively denoted binary operation in a ring. An example of a ring that is not any of the above number systems is a polynomial ring. Division often division is the same as multiplication by an inverse. Multiplication for some types of numbers may have corresponding division without inverses. In an integral domain X may have no inverse but may be defined. In a division ring there are inverses but may be ambiguous in non-commutative rings since need not the same as exponentiation. When multiplication is repeated, the resulting operation is known as exponentiation. For instance, the product of 3 factors of 2 is 2 raised to the 3rd power, and is denoted by 23, a 2 with a superscript 3. In this example, the number 2 is the base, and 3 is the exponent. In general, the exponent indicates how many times the base appears in the expression, so that the expression indicates that n copies of the base are to be multiplied together. This notation can be used whenever multiplication is known to be power associative.